Hey everyone, welcome back to the channel. Today we are diving into another exciting problem solving session. I'll break it down step by step so you can master it with ease. Let's get started. Today we are gonna solve counts, count of substrings containing every vowel and k consonants too. It's a medium problem on lead code. Now let me read the problem statement first. You are given a string word and a non-negative integer k. Okay, so we are given a word and k, and the constraints for this one is the length for the string word. It can be minimum of 5, starting from 5 to 2 power 10 power 5, and it only consists of lowercase English letters. And k can be within the range of 0 and if we take the maximum 10 power 2 to the 2 times 10 power 5 minus 5, we can roughly say 10 power 5. So what is the problem statement here? Return the total number of substrings of word that contain every vowel at least once, uh, and exactly k consonants. Okay, so the problem says that we need to find is count number of substrings such that a substring must at least contain all the five vowels A, E, I, O, U and exactly K consonants in it. And these vowels can be any number of times. A can be at least once, can be or any number of times. But A, E, I, O, U should at least present occurs one time in the given substring. If that is the case, we need to count it as one. So such that in how many substrings that satisfy these two conditions will be our answer. So find number of substrings such that contains at least one. The second constraint is exactly contra. Uh, Consonants are nothing but anything, any letter apart from this is a consonant in an alphabet. The ideal way, like the naive approach, is like uh, for a given string, let's say we generate substrings, and if we pick one substring and see if it both satisfy these 2 points conditions, then we can count it as one. And that will take a big of n cube time because n squared to generate substrings, and for each substring we are linearly checking these two conditions are satisfying or not. That is an n cube solution, but for given constraints like 10 power 5 of length, so it will be 10 power 5 times 3, which will be 10 power 15, which is not a good solution. Uh, and what we can do is uh, uh, let's start with uh, basically, let's say at any for a given I comma j, where I is a start of the substring and j will be the end of the substring. What we are doing is, let's say if we add a new character at the end, and we don't have to recalculate from I to j for the new j plus 1. uh, based on what is a j plus 1 character, we can make some assumptions. So let's say we are maintaining a window, and maybe while keep adding letters to that window, can we make any uh, as insights such that it can be solved in a linear way? So but let's try to add a first character to our window where I and j will be pointed to 0. Yeah, and for sure, uh, vowels cannot be 5 because we only added one to the one character to the window. So let's say we keep adding characters to our window, and at any point of time, two things can be possible. Either point one and point two, these two conditions will satisfy, else no, right? So as long as it doesn't satisfy the both the conditions, we can keep adding from the right. That is clear, right? Let's say at any point it satisfies both the conditions. Now what we have to, like, we have a window starting from I till j. This satisfies the both the conditions P1 and P2, like these two. I'll just make it as point one, point two. Now, for sure, this is a window uh, we can count, and we don't know later point. Let's say this is an n. Later point, we may encounter either a consonant or a vowel, right? So, if we encounter a vowel, uh, we can still, let's say there were no consonants on this part, right? And if there are only vowels, right, then we can directly have these many substrings, right? Substrings ending at here, until n. So that will be n minus j. And let's say if some consonants are present here, what we can do? So the k will become greater than k, right? So uh, like whenever we are solving a sliding window problems exactly equal to k, there is a trick pattern uh, we can follow. Like say how many things greater than k and minus how many things greater than k plus 1. If we make a difference from these two, we will get exactly how many things are equal to exactly things exactly equals to k. This is a pattern. It's because let's say how many things are greater than k, we have a count, and how many things which are greater than k plus 1. So the both common things were this one in these two, and if we make a difference, we only get exactly k things. So instead of so based on this insight, we will make a change in our problem statement, like how many substrings are there that contains at least these vowels once or greater than or equal to k consonants. So so this, let's say this function will solve this new constraints, then we can make it in a linear time. It's just an observation, and this is a common pattern in sliding window problems. So uh, it would be great if we make a note of it, like if we maintain some patterns notes for DSA, such that we can apply it uh, whenever we encounter these kind of scenarios. So it is better to make a note of these kind of things and have a problem link under this, such that we will observe these kind of patterns later when we try to solve in an interview setup. So let's try to solve this. Let's try to code this up first. Okay. And let's say, and for now, let's uh, making two count that will count a plus one. And here the return type is long. So we'll have to make sure. So return type is long. And we have a method. Okay. Okay. And we have two variables last. And we will have a result. So to tell that compiler it is a long, we add L with after the number. So this will be a result, and we run a loop. Let's say this is the right variable, and right plus 10. We also need small. Uh, so work dot char right, and we need function is vowel. Okay, and we define a vowel method and returns a boolean. Takes an input can and return is c is equal to a or c is equals to e or c is equals to a and e I y, the last one. Okay, so is an implementation whether the character is vowel or not. One very basic one. Um, we also need number of count for consonant. So number of consonants in within left and right window. And we need a map, uh, hash map of character comma integer. So the map will have key as an vowel and integer will have the frequency, how many times it occurs. So if it is a vowel, what we're gonna do is map dot put. We're gonna put the character and get out. We have a method called get out default. If the character is present, we get the count of it. Else, we'll get the default, which is zero. If you are keep inserting a new key for the first time, it will go to the default one, and which is zero, and we will increment by one. And if it is a consonant, we'll just increment by one. So uh, here we don't have to care about number of consonants. Uh, what we can do is, let's say if there is, we check for a valid window where these 2 points are satisfied, contain at least one or exactly greater than or equal to k, because we change the problem statement, right? To solve it. So we don't know. Let's say if it is equal, we count how many substrings from left to the end, and we'll try to string until these conditions are valid. If not, we'll have to reset it. So we will do uh, map dot size is equals to 5, and number of consonants is greater than or equals to k, right? If so, uh, we will count how many substrings can be there from left. So let size be the uh, these many substrings will have map dot size is equal to 5, and consonant can be greater than. Why? Because I have explained here this part. So uh, let's say at this point we have an like at least all the vowels once and some k consonants, and there can be more consonants here, more vowels will be there. So we are checking for since vowel already present, it doesn't matter vowels occurs or not, but consonants also it doesn't matter because we are checking for greater than k, greater than or equal to k, because we already found k consonant. So now at this point, how many substrings starting from I? Uh, this is a start point where the satisfies a condition, and these points can be corresponded to the answer. The answer can be n minus j, because out of n, if we remove these many parts, these are all will contribute to our answer. So that's why we are doing n minus j, which is size minus right here. And what we gonna do is we'll have to string the window. Uh, uh, we will change this the leftmost pointer and such that it will string, and see if it still validates the condition, then we'll count that many substring starting at left, right? Now what we're gonna do is we will have to string the window. So what we're gonna do is uh, mm, so again we have to check this condition. I'll just copy paste here. C is equals to okay, and here we have to do minus, and one condition we have to do is map dot get. We'll have to remove directly because we are just decrementing it, but the key is still present. So whenever the frequency becomes 0, we'll have to remove, and we'll have to decrement by -1, and we'll have to increment left plus plus, right? Uh, so this is the condition. We keep string the window until we satisfy the condition. Whenever we don't satisfy the condition, and the right will keep moving forward, right? So this will be uh, the solution for it. Let's try to run some sample test case, and we'll have to make sure this thing is correct. Uh, let's say we found some uh, size is some 7, and we are at some 5, some 6, and k is equals to 1. So we are at 6, and at 6 we satisfied some condition from 0 to 6, and this index will be become 5 instead of, because this is a 0 based. So how many substrings can be possible? Let's say if it is, there will be 2, right? So size is 7 minus 5, which will be 2. So that is, so this will be correct. Whenever we are doing some kind of counting, like we will off by 1 every time, when because we are sometimes this variable might be 0 based, and this size is based on 1 based. So always better to choose a small test case and check, and if it satisfies this condition, it will satisfy for all. So it is better to do this kind of checks. And let's try to run this first. Yeah, all the basic test cases get passed. Uh, let's try to submit this problem and see. Yeah, this got submitted, and let's try to analyze time and space complexities. So let's analyze time complexity. We declared some variables here, and this right variable is running n times, which is size of the word. And we are doing some constant operation here. Each vowel is a constant operation, and this update is a constant operation, and else what is a constant operation. And there is a while loop here, and this will run till uh, basically number of uh, characters we added so far, and we are shrinking here. So this left will go till right. So at max, we were uh, traversing the word array twice. Uh, it will go forward, and this right will go towards the end, and this left will also go towards the right. So at most two times n, which is big of n, we reduce the length of the word. And coming to the space, uh, we are using an hash map, which can be constant because at max we will be having 5 keys, that is A, E, I, O, U. So, and any other space we are using? No. So big of 1 will be the space. And this is it for the problem. And it comes under a sliding window approach. And two uh, takeaways were, whenever there is a question on substring, like count something based on some condition, uh, try to do, let's say we have let's say consider a substring, and let's try to add one more from the right, one character, and what things are changed based on the condition they're given. Try to think in that way. And another key point is, uh, if they want to find exactly k thing, try to check for greater than k things and k plus 1 things, and make uh, mm, the difference will give us the exact k things. That is a key point here. This is it for the question. And Let's meet in the next video. And thank you for watching the video. And please like and share and subscribe to my channel. Bye.